Okay, can we begin? Okay, hello, I'm Kamand. Sorry, I was taking a sip of water. I'm Beth. And today we're presenting energy-based models for continual learning, and the authors are from MIT, Baylor College of Medicine, and Google Brain.
All right, so before we begin our presentation, I just want to say that I think you guys should go check out the paper and the code. If you know me personally, which none of y'all do, but if you did know me personally, you would know that something I hate is like computer science jargon. Don't like that. But there is a computer science jargon word that I would use to describe this solution, and it is elegant. I really think this is an elegant solution. We won't be able to cover everything in the paper today, so I would really encourage you guys to go check it out.
Okay, so I would like to start our presentation with a question. In the past years, machine learning models have become capable of solving challenging problems that we never imagined were possible. But they're still far from behaving like human brain. So how do you think machine learning should change to become more like our human brains? I mean, there are a lot of things, but any ideas like how it could change with machine learning? I want your answers.
Learning by little data, little amount of data.
Okay, so there are a lot of things, but something we're focusing on today is that most machine learning models cannot be trained on multiple tasks or classes. When you train it on a certain data, you can't train it on something else. It forgets the previous task. But if we look at ourselves, humans, for example, children, when they learn how to walk, they don't forget how to crawl. When they learn how to eat, they don't forget how to walk. Us humans, we don't forget our previous skills as we learn new skills. And the problem that we're trying to focus on today, called continual learning, focuses on training models so that they remember prior skills as well as new skills. Just like any other machine learning or deep learning problem, classification is one of the primary challenges that needs to be addressed. So this is our focus today, continual learning for classification problems. There are two ways we can look at classification problems. First one is task incremental, and the second is class incremental. So in task incremental, we know the task. So assume that we're training on T1, we have task 1 here. We want to teach the model labels 0 and 1. And we have task 2, labels 2 and 3. So we know the task, and we tell it, okay, T1, tell me if it's digit 0 or 1. Or we can say it's task 2, tell me if it's 2 or 3. So this is task incremental. But in class incremental, we don't know the task. Just feed the model and increase the number of classes gradually, and it doesn't know which task it corresponds to. It has to know which label it is without knowing the task. And as you can probably tell, class incremental is way more challenging than task incremental. This can be solved with a lot of like regularization problem solutions, which we will talk about later. But yes?
Is the incremental class has no labels, but task incremental have labels? Is that different?
No. So see, here we have active heads and inactive heads. In this one, I have a head for task 1. I have a head for task 2. So when I know which task it is, I switch back and forth between the tasks. So I know, okay, it's task 1. I need to decide between 0 and 1. It's task 2. I need to decide between 2 and 3. But in this one, you don't know. You're given 0, 1, 2, 3, and you have to choose between them. And it's challenging. So the challenge with continual learning is catastrophic forgetting. Like I said before, as they are trained on new tasks, they forget prior tasks. So assume that we have 5 tasks, and we have digits 1 to 10, and we break it down and assign 2 digits to each task. And if we want to look at the accuracy for task 2, first we train on task 1, and the accuracy is really low because it hasn't seen the data for task 2 yet. And then when we train on task 2, we get a very high accuracy. And then as we train on new tasks, it goes really down because it forgets about task 2. Same for task 3 and all the other ones. Okay.
How did you attach this? There we go. Okay, so this is another way to visualize catastrophic forgetting, and this was taken from the paper that we are presenting on. So the first thing we see up there is energy land map, and it's energy land map of Softmax-based classifiers. It's a little confusing. Well, it was confusing for me, so to interpret how to read this thing, but basically it is giving the negative probability of the class. So it's prediction of the probability of it being a class, but we're taking that and negating it. And you'll see the reason why later in the presentation. But what you need to know for now is the closer to 0 or at 0 is good, so the darker is good. Because of that, we want our line on the diagonal to be completely black and all other places to be that pinkish red white color, because we do not want to be predicting the incorrect classes with a high probability. Does that make sense? Perfect. So as we can see for Softmax-based classifiers, we have dark stripes on those horizontal lines. After task 9, it's predicting the task 9 classes with a lot of, it's saying, hey, this really is those classes. That horizontal line is dark. Same thing after task 10 is trained. It's really only predicting the task 10 classes with a lot of probability. That's bad. We don't want that. We want the diagonal to be dark. Here's another way to visualize it. It's a little bit easier to interpret. It's just like these little pie chart probability things. Not a pie chart, but almost the same thing. And we're seeing that as we're moving forward in the tasks, it is not predicting the classes that were learned in the previous task. So it's catastrophically forgetting them, no longer predicting them. All right, so here's a meme we made because we wanted to be a little funny. Here we can see Softmax-based classifiers. We can see it has the already correct or actually correct class, but instead it really wants that random class that it met like 1 second ago. Like it wants the shiny new thing. So that was a meme we made.
I have a question in the last slide.
Yeah, you mean not that one,
No,
right?
not that one. I understood that.
Okay.
So in that graph, the label are named from 0 to 100, I think, on
Yeah.
the y-axis. And before you said that, is it an MNIST data set? So we have 10 classes, right?
No, I believe this is the CFAR.
Oh, that's a CFAR?
Yeah, sorry, we should have
Okay.
said that. My
Okay,
bad.
yeah.
That would be confusing.
Okay.
Yeah. Okay, well, good thing you don't have questions about that.
Nah.
Okay, so here are some previous works that have been done to try to mitigate this catastrophic forgetting thing. The first is regularization. However, it doesn't perform well on class incremental learning problems, which is what our paper is focused on. Also, the authors of the paper said that it doesn't actually work well in practice, it only works well in theory. And we'll get some numbers to show you guys to prove that later on in the presentation. Then there's memory. I mean, that's a pretty obvious drawback. You need memory. And then complex architecture. No one wants complex architecture. At least I don't want complex architecture. I don't know what you guys want. But I don't want that. Like dynamic neural networks don't want that. And one of the beauties of energy-based models is they do not have complex architecture. It's pretty simple. We can look at the architecture later if we want to.
All of these models that we just described, Beth just described, they
Oh, yeah.
all use Softmax.
Yeah.
They're Softmax-based.
Well, yeah, they either use Softmax-based or they use some sort of normalization or iterization. Sorry, I forgot to mention that. Thank you, Kamand.
Do you know the specification for the training objective function, the label for the energy-based model?
We're getting to that. Are you talking about what is the training objective?
Yes.
Yeah, we'll get to that.
Okay.
Great question. All right, so this slide is just here. It's just here if we need it to go back to later. All right, you guys should know about Softmax-based classifiers. And I'm going to start talking about why they cause catastrophic forgetting. What is it about them that causes that? So, as we see from Softmax-based classifiers, we have this thing that normalizes, it gets the probability and it normalizes it against all other probabilities. So each class is trained in reference to all the other classes. The downfall of that is that all of the logits are kind of married to each other in that equation. You can't really separate that. So if you're trying to raise so if we're looking at task 2 here, if we're trying to raise the probability of task 2 and 3, what we're going to have to do is go back and raise the probability of that equation. In order to do that, we have to go mess around with all of the numbers here of all the classes. And so that causes the neural network to push up the probability of the correct classes, but down the probability of the classes that may be correct in the future for testing, but right now are not being seen because the task has been moved. And since we're moving tasks, we don't have the chance to push that probability back up again. So it's just going to be pushed down to 0, eventually get to 0 or really close to 0, and then stay down there, unless we use some sort of replay. But we're wanting to avoid doing that.
So as we do this mechanism, every time we change the task, we play with this formula?
Yes, so this is used in training for Softmax-based classifiers.
Each task, we change the task, each time we change the formula, so we bring up the probability of other classes and bring up the probability of our class.
Yeah, exactly. So the
Our
formula
task
itself isn't changing, but we're pushing up that probability of the tasks that we're training on, and then pushing down the other ones because we're.
This is happening every time we change the task.
Yes, yeah, and that's what causes catastrophic forgetting.
So why don't you just simply train different neural networks for each of the tasks and combine them?
That would be complicated architecture. We don't want that.
Oh, I have a question.
Yeah.
So from his question, because we are class incremental learning paradigm, so we just have the present of the task at the time that we say. For example, at T0, we just have a task 1, T1, we have a task 2, so we don't have all the tasks at the same time, so we cannot do that. So we cannot train all the model and combine them.
Mm-hmm. Yeah, the
so
model.
Actually, we just have one model, and the model evolves over the time.
Yes, yeah, that is what we were wanting to do with energy-based models. Thank you. Yeah, so does everyone feel comfortable with this?
Can you clarify, when you train on task 1, so there are 2 labels, 0 and 1.
Mm-hmm.
Task 2 labeled 2 and 3,
Mm-hmm.
task 3 labeled 4 and 5. So when you train on task 2, the softmax is over just 2 and 3, or it's actually over 0, 1, 2, 3?
0, 1, 2, 3. Yeah.
So when you train on task 3, the softmax for task 3 is 0, 1, 2, 3, 4, 5.
Mm-hmm. Right. Yeah. Yes. Okay. Sometimes I get nervous and think I'm going crazy. Okay. All right. So that's a problem with Softmax. Energy-based continual learning, we're trying to fix that. So energy-based continual learning is good because it doesn't require extra memory, doesn't require complex structure. It's just one model, very simple architecture. It performs well on class incremental tasks without using replay or relying on stored data. And it performs well without task boundaries, which is called task agnostic. We'll talk more about that later. All right, so here's our energy-based model. We've already seen this, I think it was last week, 2 weeks ago maybe. It is based on the Boltzmann distribution, which does have a definition of physics. That's really interesting. You should go check it out. We've linked to a resource to do that, but this is not a physics class. So we're not going to talk about it too much, other than what you need to know is that the probability of state X is going to be inversely related to the energy of state X. That's kind of something we all know intuitively. Things seek lower energies, and that one, they're more probable in nature. So the biggest difference between energy-based models and models that use Softmax-based classification is that energy-based models are going to have one output. It's going to be one scalar value. It's going to be energy right there. One output, energy. So you know how normally we have, if there's 10 classes, we have those 10 nodes, and each of those nodes are the probability of those different classes. We don't have that anymore. We have one little output. It's going to be energy, and that's really cool, actually, because we can have, however many classes we want, still one output, energy. And if you're not thinking it, you should be thinking it. Well, what about Y? How do we tie this in with the label? Like, how do we tie in our input to the label if we're only having one output? And this is how EBM looks. We're actually taking y as an input. It can be called a filter gate, conditional gain is another thing we can call it. It's basically taking y and it's incorporating it into architecture. Again, we can go look at the architecture later if we want to, but it does it through various methods, and our authors actually tested out different ways to incorporate y into our architecture. But what it's doing now is instead of saying the probability of class X corresponding to Y is inversely related, the probability of state X is inversely related to the energy of state X, it's now saying the probability of class X corresponding to Y, or X with Y, is inversely related to the energy of X corresponding to Y. So it's going to take X and Y together, and it's going to give us an energy that represents the energy of them together. Any questions? Okay. Oh, sorry, no time. So here's our EBM loss function. It's pretty similar to the other loss function we're familiar with, except for right now we're trying to minimize energy of the actual correct pair and then maximize energy of the incorrect pair, because we're predicting based off of the minimum energy. So does anyone see a problem with this? What is the problem, Kamand? Good. Oh, wait, was David going to say something?
I was just going to say that it could be a local minimum get stuck in, but I'm just...
Not the problem we're addressing. Okay, Kamand. Sorry.
Can answer your question, Mary Beth.
Yeah, Kamand can answer my question. That was a good answer.
Okay. So you notice how we're summing up all the negative labels here? So we're still going to have the same problem that we had in Softmax, because we have all the negative labels and they're being summed, and we're trying to maximize this. So we will have catastrophic forgetting again, even with this loss function. So the authors of the paper modified this equation to this you can see here. So instead of summing up all the negative labels, we just use one negative class label and use that for the negative pair. But how do we choose this negative label? There are several ways we can do this, and the authors assessed 3 different methods to choose these labels. The first one is to choose your Y from the list of all the negatives that the model has seen. And the second one is just use negative labels from your current batch. And the third method is to just use one negative label. So assume that we have 2 tasks here, and I'm training on 3, 4, 5, and my correct label is 5. If I want to use the first method, what are my negative labels? 0, 1, 2, 3, 4, right? If I want to use the negatives from my current batch, it would be 3 and 4. And if I want to just use one negative label, it would be 3 or 4, right? So notice how the accuracy improves as we have less negative labels. So the authors concluded that as we have smaller amounts of negative label, we can minimize the suppression of the previously learned classes. So this is the learning objective of this model. What we want here is to have a very low energy for the positive pair and a very high energy for the negative pair. So for example, we have 0 here and we have infinity here. So the ideal learning objective, the loss for us would be negative infinity, right? We want it to be as small as possible. But why does EBM actually help prevent catastrophic forgetting? Well, just in case you've had catastrophic forgetting and you forgot what Mary Beth said 5 minutes ago, I will recap. And so in Softmax, since we're looking at the probabilities relative to each other, we are decreasing the probability of the classes that the model previously saw. So they kind of die. The probability goes to 0, and they are no longer in play. But in energy-based models, we decrease the energy of the correct class and keep the negative energies high. So they stay there. They don't die. And so there's more freedom for the model to assign energies to the labels. so it doesn't forget previous labels, previous tasks.
Yeah, and I want to add something to that really fast. You have a question?
I was just wondering, is the idea that this is sort of like sampling the negative ones, just choosing a few small selections?
Yeah, that's exactly what I was just about to add. That also helps. We're not taking and shoving up the energies of all the negative ones. We're just taking one, and that's why we see on that 3 different comparisons of 3 different methods, the one that only selected one is best.
Yes.
How do you choose one? Will you tell us next? Or how do you choose that one negative?
It's
Random.
It's random.
yeah.
So we have 3 or 4, it's randomly chosen. But yeah, if for example we were training on 3 and 4 and then 0 and 1 and 2, then these 2 methods would have been the same because we have just negative label in the batch. Okay. It's you.
Oh, this is me. Okay, so there's our architectures again. Again, I'm just leaving this slide here in case we need to go back and reference it. So we're going to talk about the experiments that the authors did to prove that this is a good idea, that this really is, as I called it, elegant. All right, so here we are back to the energy land maps here. So as we can see, EBM does not have that characteristic dark horizontal stripe. What's happening is if it is class 10, it's predicting class 10 with the that high probability. 20 goes to 20, creates that diagonal like 1-to-1 line, that slope of that 1-to-1. So we don't have that characteristic dark stripe anymore that we see in SBC. And the reason that we did negative probabilities for SBC is because energy wants to be low, that would be closer to 0, and that's why we had to negate, or the authors, I didn't do it, I had to negate those probabilities to make those energy land maps match up. All right, here's our nice little pie chart kind of things. Again, as we can see, EBM retains and does predict the old classes even as it moves forward in its tasks. That one's a whole lot easier to look at, a whole lot funner to look at. Another thing is that it's not predicting classes 9 and 10 with a huge, it doesn't dominate that little, it's not a pie chart, I forget the technical word for it, but it's not dominating that probability distribution that we see. We still have the other classes pretty well represented. It's not just 9 and 10 taking up 90% of that. All right, here where we get to the more hard numbers, so we move from qualitative to quantitative analysis. So we can see down here that EBM outperforms all of the other methods on these 4 different data sets by a pretty high margin. It is often 2 to 3 times better than the next leading method. I told you guys that I would show you guys that regularization doesn't actually work. So we have our EWC, that's elastic weight consolidation, online EWC, synaptic intelligence, and learning without forgetting. Those all kind of use some form of regularization in their own way. So we can see that regularization, even though it was a previous solution, EBM still really outperforms it. Bayesian gradient descent is actually pretty interesting. I was reading that paper a little bit last night, but as interesting as that paper was to me, does not compare to EBM.
I have a question here.
Yeah.
So most of them are about the regularization, right?
Uh-huh.
So, but they don't have the comparison with the replay strategies.
I'm sorry, what now?
In continual learning, we have a replay strategy
Oh,
to
yes.
prevent the catastrophic forgetting.
Uh-huh.
But you can see if you have a 10 tasks continually,
Uh-huh.
right? So your regularization definitely it would not help because we have 10 tasks.
Uh-huh.
So,
So you're asking about replay?
yeah. So
Yeah.
but
We'll
they
get
don't-
to that.
Mhm.
Yes, great question. We will get to that. Yeah, these are specifically non-replay methods. That is correct. And the authors did that on purpose because EBM doesn't have to rely on replay. So that's why they tried to compare like that. Then they're like, okay, so we have another question, and other people might have other questions. Why does EBM perform well? Like, what is it about EBM that makes it perform well? And one of the questions is, was it actually EBM's loss function, or was it just we just chose a good architecture? So what they did is they took these other methods, they used the method's architecture, and all they did was replace the loss function of the method with a modified version of their own, and we can see it did improve all those methods. So it wasn't just EBM's model architecture, it was in fact the loss function that did cause the performance to improve. Down here we see it with different label conditioning architectures. That's a really confusing word to me, but that basically just means how they incorporate Y into the model. And they have their architectures really well spelled out in the paper. We can look at those later if we have time. But basically all it's doing is placing in Y at different parts of the model, either at the beginning, at the end. Sometimes they use a softmax, sometimes they just embed it. And it's really well spelled out in their paper, and they also have some code. But yeah, as we can see, placing Y in different places does change the performance. So that's also an indicator that that does contribute to the performance, and it can be used to improve the performance as well. So both matter. Yes, both matter is the conclusion of this slide. All right, so here are more comparisons. We have SBC. You can see that its accuracy of the different tasks dies as soon as it moves forward to the next task. SBC plus the loss function, so minus softmax plus our loss function, so SBC, but not really SBC. It improves the accuracy. Still not great, but look, it's not completely dying. And then EBM, the accuracy is up. It stays up. It doesn't really look like it's dying. I mean, it might go down a little bit, but this is much better than this, and this is much better than this. So, great.
Come back to the last question of Professor Nguyen about how can we choose the negative label. I see we have the table number 3. In that they have the 3 strategy. The first strategy, like they use the own sin class as negative label. The second one is current one as negative, and the last one is random. So do you have any talk about that one?
Yeah, we talked about that. We had a slide on that.
Yeah.
But we can go back after we finish, if that's okay with you. Okay, so I think a very interesting question to ask here is, so how many tasks can we train on EBM? How much can it handle? And let's look at EBM with different tasks and also different methods. So they used C400 and split it up to 5 tasks, 10, 20, and 50 tasks, and compared the performance of all these methods and EBM for all these tasks. As you can see, all of them have lower accuracy as we increase the number of tasks. But still, even for example, for 50 tasks, you can see SBC has 1.91 and EBM is like 13 point. I mean, it's still that low, but even then, it has much higher accuracy than the other models. Yeah.
Sorry, I was going to say, I think what's also important here is it doesn't, I mean, you can kind of look at the numbers and calculate the slope in your head or on your phone, but it's not like the accuracy of EBM and the other methods are like eventually converging after 50. EBM still remains about 2 times better than the next leading.
Yes. And okay, we get to replay. Replay is a song, but it also matters in continual learning.
I actually listened to that song while I was talking to calm myself down.
So what is replay? So like our friend said before, a method to help continual learning is to use replay, which is as we're training on new tasks, we sample data from previous tasks and feed it to the network to help it be reminded of the previous tasks that it learned. But to do this, we need to store data from the previous tasks. So we train on task 1, and then we store it, and go to task 2, sample from task 1, feed it to the model as it's training on new tasks. And it's, as you can probably tell, it's very computationally expensive. And the purpose of EBMs was so that we don't have to use extra memory to store the data. But can we use EBM can we use replay on EBM? That's the question. And I think it's say that replay to machine learning models, it's like us studying for exams, and it's also a question that how do we choose this data from previous tasks? What if somehow it's not the correct review part for it to review? But luckily, EBMs are very flexible, so we can use replay with EBMs. And here you can see the result. It is very impressive to have such high accuracy on these data sets. It's about higher than 90. But let's look at EBM without replay and SBC with replay. You can see that sometimes, for example here, they're about the same. And the other times also here, they're kind of about the same. So sometimes EBM without replay has the same performance as SBC with replay. So that's how powerful EBM is. And so definitely replay can be used with EBM. So far we have talked about boundary-aware settings. All the experiments that we showed were in boundary-aware settings. But what is boundary-aware? Boundary-aware is when the model knows the exact boundary, the exact sharp boundary between the tasks. And a lot of previous work on continual learning relies on these boundaries. For example, for the ones that use memory or regularization. They need to know when the next task begins so they know how to store the model and update it and do different things that they do with their methods. But that's not very realistic. Boundary agnostic settings are more realistic in real life. We have, for example, we're training on one task, and then we gradually start training on task 2. And then we were training on task 3, and then we start gradually training on task 4. So let's look at EBM's performance in boundary agnostic settings. The accuracy is very high. You can see here, for example, for MNIST, it has a very high accuracy. And this is not something that the authors mentioned, but we were talking with Mary Beth, and I think boundary agnostic settings are way harder for other methods because they rely on the boundaries. But for EBM, because it doesn't rely on the boundaries for its classification, it's even easier for EBM. It's sort of like replay because you're repeating previous data or like mixing it up, so it becomes easier. So if you look at the accuracy of EBM on boundary-aware settings, it's lower than EBM on boundary agnostic settings. And I think that's very interesting. Also something that you might have noticed already is that MNIST is a way easier data set for EBM, but C400 and C410 are more difficult because of the nature of the data sets. I guess numbers are easier to classify. So in conclusion, today we introduced energy-based models. Energy-based models have a natural way of being able to expand and dynamically grow as we increase the number of tasks or classes. And they help prevent catastrophic forgetting, which is a big problem in continual learning. One drawback of EBM is that during testing, you need to calculate the energy for each negative label to be able to classify. And that's one drawback. And the authors suggested that we can maybe in the future have hierarchical models. So for example, you decide, okay, is this a vehicle or an animal? And then between animal, is it a cat or a dog, to reduce testing time. And the moral of the story is to not be afraid to be abnormal, like EBMs. Maybe that's good for you. And if you want to read further, these are some links, our references, and our acknowledgments. And if you have any questions, we'd be happy to answer. Yes?
So on the replay with EBM and